what characteristics are we looking for when we're picking out a mid-range driver? And we're not talking about name brands here. We're talking about characteristics of the driver. What can you look for to know what to expect from that driver? As you can see on the drivers that are in my Tahoe, this one is extremely rigid. There's not any deflection in this. When you push here, the whole cone moves together. That's the toughest spot. Now on these machetes, you get a little bit of deflection. See that? But not much. And now these drivers, the Pro Audio mids, are always going to be really thin on the cone, and so that's to allow them to be as light as they can be and be as efficient as they can be, so they get really loud. But having said that, this one is pretty rigid for this type of driver. Okay, we're going to talk about two basic different types of drivers and two different quality levels. So for the first side, we've got an inexpensive woofer and a slightly better woofer. And on this side, we've got an inexpensive Hayanka coaxial and a much better Memphis coaxial. Now, on the face of it, these both do the same job, but in reality, they are completely different. So first, I'll show you a couple of things you can tell right off the bat. If you reach under the edge of the driver, right to this point where your surround meets your cone, and put your finger under there and press up slightly, you can see that it deforms really easy. And push it back here, see how it deforms? The cone doesn't move much, but it deforms a lot. On this one, if I do the same exact thing, it deforms a little, but mostly the cone moves. Back here, that's because the cone is much more rigid. And a rigid cone is always going to give you a better pistonic movement, a better response overall, with less color in the reproduction of sound. The same thing with the coaxial drivers. Under the edge of the Hayanka, see it just completely, it doesn't move hardly at all, it just deforms. Under the edge of this Memphis driver, let me find a spot here. Look at that, the whole piston moves. There's no deflection, no deformation at all. You can't even tell where my finger's at under there. And it's because that cone's very rigid. The material they make it out of doesn't have any distorting elements. And whenever you're moving back and forth, that means it's not going to add any extra sounds to the sound it's trying to reproduce. And that is the whole goal behind trying to reproduce music through a mechanical device, is to not add anything to the sound and to just reproduce the sound as it is being fed into the equipment. So if a driver does have a resonance, if the cone does resonate, meaning vibrate by itself, think like a bell, okay? If a driver bells or rings, it needs to be outside of the frequency that driver is intended to reproduce. So for example, if a woofer cone has a ring to it, a resonance to it, then it would typically be up, 3,000 or 4,000 hertz or higher. Then it's never going to be an issue, because the woofer's never going to be playing at that resonance anyway, so you're not going to get that color. I'm not talking about the resonant frequency of the entire driver right now. I was talking about the resonant frequency of the cone. Now the driver's RF, or resonant frequency, is all the moving mass. And whenever you're considering all the moving mass, you're talking about an entire system that's moving, not just the cone vibrating in itself. And I'll explain the moving mass, or the resonant frequency of all the moving mass of a driver. Like whenever you're pushing somebody on a swing, the rate that person naturally swings back and forth, even though they're getting smaller and smaller, that that rate will stay the same even though the distance is shorter. They'll just swing slower, right? So they're going to hit that center point every time. That point where that person hits that bob each time is the resonant frequency of that person, period. If you put a larger person on the swing, more mass, it's actually going to be a slower frequency. And if you swung the swing by itself with no one sitting in it, it's going to be a very fast frequency. The resonant frequency of the swing is going to be dictated by the mass that's on the swing. Same thing with a speaker or a driver. The mass that you're moving back and forth and that has its resonant frequency. The more mass there is, the slower that frequency is going to be. You want to avoid playing the driver at its resonant frequency because it's going to move more at that frequency and it's going to be out of control. So it's not going to be optimal. Does that make sense? You want the same work to be done across the frequency range so that the reproduction of sound is linear. If you play that same amount of power you're putting on it, whenever it gets to its resonant frequency, it's just going to go. And so that means that when you hit that resonant frequency and it starts really moving, it's going to produce a much louder sound at that point, and it's going to sound completely wrong at that point. Or it's going to go into have a more likelihood of mechanical failures. This isn't normally an issue, and you probably won't run into this, but it's something to consider. If you're planning on a driver play 60 hertz, which is pretty low for a mid driver, but let's say you're wanting to do that, and the mid driver has a resonant frequency of, say, 68 hertz. When you hit 68 hertz, it's going to make some weird sounds. It's going to make some off-color sounds because it's going to really be cranking out the movement. And as you start trying to blend that in with your woofer and everything else, you're going to hear these weird peaks of certain sounds that are just going to be wrong, and you won't know why. And it's because that driver is getting all excited about playing at 68 hertz. See what I'm saying? So you don't really want to get that driver in its resonant frequency. You usually want to cross over outside of that. So looking for a driver's resonant frequency and knowing what you plan on doing with it is going to be important. Other than having a very stiff cone, having a light cone for a mid driver is also very important. And the war between light and stiff has been going back and forth for a very long time. Manufacturers have been trying to find materials that are both light and stiff at the same time because they are more accurate in reproduction. The only exception to this rule is when it comes to subwoofers. Subwoofers are a lot more compliant when it comes to weight of the mass because the frequency they're vibrating in is very low. And so having a more mass sometimes actually helps. This also is the case for mid-bass drivers. There'll be something that's the size of a 6.5 inch driver, but it'll have a lot more mass in it and also be a lot stiffer to handle playing lower frequencies better. You give up some of the high frequency response, but you're gaining low frequency response. You can't have the best of everything. So there's always sacrifices to be made. And depending on what exactly you're wanting that driver to do, the characteristics will come into play. Picking the driver with a lower frequency response, a lower resonant frequency, is going to offer a driver that plays lower in the overall frequency range. And of course the opposite whenever you're picking a driver for higher frequencies. And the spec sheet will usually tell you this, but if it doesn't, again, just some quick inspection of the driver, physical characteristics, will tell you most of what you need to know. And you can get in the ballpark. So 6-inch mid and 6-inch mid and 6-inch mid does not mean the same thing. They can be all three totally different and have totally different characteristics and be good for totally different things. Understanding what makes one driver better for one thing than another is a big deal when it comes to putting together an audio system. Keep that in mind.